My name is Joshua Soteris, and this is my video for week one. Basically, the material that I'll be covering is what I learned and what I understood from the videos. And that includes what neural networks are and what ReLU is. So, the first thing to understanding neural networks, I first had to understand what the difference is between machine learning and deep learning. So, machine learning is basically an umbrella where deep learning falls underneath. But machine learning is the objective of performing a task or programming something to perform a task without being told what to do. And this can go for cases such as detecting email spam or not spam, right? And we can do this, this could be done through algorithms, as we may know. But deep learning is basically a subset of machine learning. And you could think of it like a more evolved version of it because it uses these things called complex neural networks, which mimics the brain. And its purpose is to look through unstructured data like images and text. So, for example, looking for a car and detecting if like for example computer vision and cameras, if the camera's seeing a car, how does it detect that it is a car? So this is where deep learning comes in. So the brain, I needed to understand why how the brain inspired neural networks for deep learning. And basically, a neuron in the brain is a nerve cell which generates like electrical signals, and from one neuron connects to another neuron, and these pathways are reinforced through experiences. So, for example, a basketball player dribbling, those neurons are going to be reinforced compared to other pathways because of how much electrical signals are fired between them. So this comes into plays with like creating patterns or understanding patterns, and this comes into our senses such as like learning, our motor controls, and tough decisions. So this is what inspired basically neural networks in deep learning. So how do we replicate neurons firing like electrical signals in a computer? We use like Boolean values. You could think of it Boolean values like 0 or 1. So 0 not firing, 1 for sure firing. But um, there are values between 0 and 1. So there could be 0.54 or 0.49. And basically, the closer the value is to 1 is what is considered the closest to activation or lighting up or firing electrical signal between neurons. So to understand furthermore into neural networks and how it's made up of like three main layers, or category of layers actually. First, we have the input layer, the hidden layers, and the output layer. So with the input layer, basically there's no calculations or transformations, and I'll more elaborate more that in the next few slides. But basically, each of these neurons in the input layer is just raw data. So if we were trying to recognize like a car, like each of these neurons would represent like maybe a pixel of an image of a car, and maybe like um, the curves of a car or something like that. So the activation leads to the next neurons. So give me 1 second. Okay, I kind of messed up my slides, but basically, I want to talk about the hidden layer. The hidden layer is one of the most crucial parts of the. Let me see why it's not there. So a little bit technical difficulty, but no problem. Basically, the hidden layer is what it basically trains or determines kind of how to identify this car object, right? So if like the camera is seeing a car, how does it tell it's a car? It's through each of these neurons, and whatever instance is closest to the next or activated will lead to the next neuron. So each of these neurons have a thing called parameters, and each of these parameters can be filled with either these things called weights or biases, where us as users can adjust these to better train the model, if that makes sense. So, for example, so what are um, weights? Weights is just like it's the number that we adjust so we can adjust whatever values are within the neurons. That value from 0 to 1. And then biases, every neuron has its own biases. So we can like pick those individual biases and adjust a specific type of neuron instead of one of them. So you could think of it like weights apply to all of the neurons, and then biases only apply to specific neurons. And these can be represented through a vector and a matrix. The matrix being the weights, and the vector being the biases. So what is the output layer? And I just had a little meme here, but it's basically the final answer and result from all of that neural activation. So in this diagram, technically, this is supposed to choose which of these best neurons resemble what we're trying to look for. So let's say if this one looks like the car the most, it'll pick this one and have this as the final result. So in summary, neural networks is just a big function, and I kind of just like reference Gojo. Basically, you have an input and then you have an output. So during this input, you can adjust the parameters such as um, the biases and weights to get an output. And going over what I was talking about, so biases, yeah, so biases is just a number added to weighted sum of inputs before. It's kind of like just readjusting and adapting the um, the neural network, the output we want closer to the actual target we want. So if it's detecting a specific type of car, but not, for example, Toyota, but not a Ford, then we can adjust those weights or biases. And just for more clarification, like um, the weight is an activation of how a neuron affects the next um, activation. So training is just adjusting these features, and the thing is, when you're doing this, is not to think of a black box. So not to plug and chug, but to understand the parameters, so like the weights and the biases of what you're adjusting. So each of the way the weights and biases are calculated in order to do the activation are through functions. So you can think of each of these neurons having functions. Um, the most commonly or the most old school function used was the sigmoid, where it squishes a value between 0 and 1. And this was used in machine learning for logistic regression, so either like true or not true, true or false. And this was like you can see how like this could be used for the values for 0 and 1 for like firing a neuron or not firing a neuron. Um, so the thing is today is it's too old to use, so it's like difficult to deal with, meaning like it takes a long time to compute. It's not very optimal. So this leads to ReLU. And ReLU basically, to understand it, we have to first understand the universal approximation theorem. And basically, what this is saying is that you can always approximate a function if the activation function is a non-constant, continuous, and bounded. So the theorem is just suggesting that any function, for example, this image right here, can be approximated. Um, you can think of this as a neural network. So, but to approximate it, if we were to use a sigmoid function, it would just take too long because we'd have to do each individual point. So this is where the ReLU function comes in. Um, this is what it looks like. Has a max of 0 to the value of x. So x can be whatever that's defined. And basically you're going to take variations of this function to fit a specific type of function. So like I said, we can apply these basic algebra transformations to the functions to adjust the ReLU in order to make a great approximation. So I know this is the part I was kind of confused about. Like the best way to think about this is orange line here represents a neural network, right? A function of a neural network. We have an input, then an output, but each of these points can be considered a neuron. So we just want to find the best approximation. So like basically when we're training weights or biases to have the best fit. So as you can see, these are different ReLU functions, and by adjusting, like the function, we can have it fit. And this is just more of an example. So this function can be approximated using, yeah, a series of straight lines, which is the ReLU. And basically that's what we did in the previous slides with this function. It's just use a bunch of ReLU. And the neural network representation of this is just that, like each ReLU corresponds to a node. So each like node, the ReLU function is applied instead of the sigmoid, like how I mentioned previously. And depending on how we can best approximate, meaning best apply the weights and biases for that specific neuron. So yeah, and the reason why is like if the function was simply just like a linear function like y equals x, the neural network would only be able to represent linear combination of the inputs. So without a nonlinear activation function like ReLU, neural networks cannot approximate nonlinear functions. So activation functions are crucial for creating piecewise linear functions. So yeah, like basically piecewise functions is just like taking small points in the graph from one point to another segment. So like from here to here, that would be considered one piecewise function, but which could be considered, which we would use a ReLU for. And that basically sums up my presentation. Thank you.